Co-host ready? Okay, so if you're ready, we can start. Yeah. Okay.
Okay. First,
Can I introduce you?
yeah, thank you for having me. My name is okay. Sorry.
Go ahead.
My name is Omid Tavakol. I'm a first-year PhD student at University of Toronto. I want to talk about artificial electric field and electron hydrodynamic. This work is done by collaboration with my supervisor, Professor Yang Baek Kim, and you can find the paper with this archive number. We will hope that will be published soon. Okay. To begin with, I want to talk about my motivations about this work, and then I want to have a brief interview on Berry curvature. Then I want to talk about the effect of Berry curvature in equation of motions, and how these equation of motions can change the hydrodynamic equations and give rise to new hydrodynamic coefficients in non-center symmetric systems. Finally, I want to use a simple Hamiltonian model to see these calculate these coefficients analytically and see the novel contribution to transport current. Okay. Let us start with a beautiful experiment done by Carl Landsteiner and his collaborators about experimental signature of the mixed axial gravitational anomaly in the Weyl semimetals. What they've shown in this paper is that there is an anomalous contribution to transport coefficients or thermal conductivity in the presence of magnetic field, and this anomalous coefficient is proportional to b squared, and you can see there are some contribution coming from the anomaly coefficient c and cg. There is a strong connection between Berry curvature and these anomaly coefficients. So let me introduce what is Berry connection and Berry curvature. In a system with a, if you have a Hamiltonian with, let us say, a set of parameters, I call them R, then you can introduce a Berry vector potential or Berry connection as this quantity here, and n of R is your ion state of the Hamiltonian, which can vary with your parameters. Also, it's useful to define something similar to field strength in electrodynamic, or something like this, which is the gauge field tensor for Berry connection. We call it Berry curvature. Another example, now it's useful to see how this Berry curvature is related to the anomaly coefficient that I've showed you in the first slide. There's a beautiful paper with Son and Spivak about chiral anomaly and classical negative magnitude resistant in Weyl metal. What they showed is that the conservation law of particle number in each of these touching points in the dispersion relation of the Weyl metal is this equation. And you can see here, if you go to, for example, infinite tau, if you take the limit tau goes to infinity, this contribution goes to 0, but still we have some non-zero contribution coming from the well-known chiral anomaly proportional to E dot B. And this coefficient here, K, is actually defined by the Berry curvature. In this paper, they assume that their set of parameters is the lattice momentum, which is well defined in Weyl semi-metals. And they defined Berry curvature something like curl of A. Finally, they find the anomalous contribution to transport coefficients again, which is exactly proportional to B squared. And there is a coefficient of anomaly related to Berry curvature here. Okay, but we can ask what can we do in the presence of interactions? When we introduce interactions in our problem, then your set of parameter, you can expand your set of parameters to not only k, but k and omega. And so when you have this omega dependency in your vector, in your gauge field, then you can also define something like artificial electric field and artificial magnetic field. And in this way, your we can say effective equation of motions of your quasi-particle would be changed something like this, which is shown by Shindo and Balance in 2007. And it's also useful to say something about the symmetry of this combination here, or you can just see this Berry curvature here. Under time reversal symmetry, the Berry curvature is odd, which means omega minus k goes to minus omega k. And under inversion symmetry, omega is even, which means omega minus k is omega k. And if you notice, if you have both of these symmetries in your system, then you find zero Berry curvature or zero artificial magnetic field. So if you want to look at some topological contribution to your transport coefficient, you need to break time reversal or inversion. In previous example, we actually the external magnetic field break the time reversal symmetry, but we have inversion symmetries. But in our work, we want to concentrate on non-central symmetric system in which we break the inversion symmetry, but we preserve the time reversal symmetries. Okay. Now let us start with usual Boltzmann equation. In this Boltzmann equation, I just plugged in the r dots and k dots from the equation of motions from the previous slides. And by using Boltzmann equation, you can find, let's say, quasi-conserved quantities like momentum, in which you can just multiply the Boltzmann equation by momentum and integrate over the momentum space. In this way, by doing that, you can compare these two equations. This is the usual hydrodynamic equation for energy momentum tensor. And by comparing these two equations, you can find the definition of P, the density of momentum, and the stress tensor, which is pi ij here. And you can see there is extra contribution coming from both artificial magnetic field and artificial electric field. Okay. Now to say about constitutive relations in hydrodynamic, those two contributions coming from the artificial magnetic field and artificial electric field give rise to two new coefficients. You can call them CIL or KLG here. This CIL is new coefficient found by Toshio and his collaborators in 2020. And this KRG is something that we found in our paper. Also, you can do the same thing for transport current and find the constitutive relation for current density. And by doing that, you can find four other hydrodynamic coefficients. Call it D, F, I, and G by these definitions. But I should mention that these are somehow related to these KLG and C. For example, you can see this IJK here. If you just take the temperature derivative of this KLG, you can find this new hydrodynamic coefficient. So they are not really independent. Okay. Now it's useful to see how this coefficient can contribute to conductivities. At first, I should mention that there is no contribution to linear conductivity, but in non-linear regime, we can see some novel contributions. And these contributions are the contributions that coming from the artificial magnetic field, which we are interested in. This one is the I think actually electric conductivity and other conductivities for in non-linear regime. Okay. Let us use a simple Hamiltonian model to calculate some of these coefficients analytically. We consider a Hamiltonian which break the inversion symmetry at first, and also we need to introduce an interaction to have the omega dependency in our wave function. The simplest interaction would be electron-phonon interaction in our metal or in our system. And we just want to find the actually the effective Lagrangian for this model. And you can see the self energy here, actually first order correction to self energy can provide this omega dependency in our system. And actually this self energy corresponds to these two Feynman diagrams. Okay. Because we have, actually I should mention that here, this tau y, tau x, and tau z are Pauli operators. So we have 2 degrees of freedom for each alpha, and alpha is +1 or -1 for indicating each value in your system. Okay. Now you can just expand your the real part of your self energy in terms of Pauli matrices, and in this case you can see your effective Lagrangian is not diagonal anymore for any given k and omega point. So you need a projection operator, let's call it U, k, and omega, to diagonalize this quantity at any given k and omega. And actually this operator, this projection operator, is something that defines your artificial magnetic field and your artificial electric field. In this way. And actually it's not hard to find this projection operator because you have a 2 by 2 matrix, and that's that's easy to find to the projection operator. Yeah, by doing that, you can find the results of those coefficients that I showed you earlier. For example, curly G is, you can calculate this analytically, and curly G is this quantity, where f is the slope of these two functions at omega equal to 0. Actually, because the S1 have a slope equal to 0, they don't contribute to curly G. But for example, S2 omega can contribute with a finite with a non-zero amount in your transport coefficients, or in your anomalous transport coefficients. Okay. In conclusion, we showed that if you have interactions in your system, you have additional artificial electric field, and this artificial electric field gives rise to modification of equation of motions, and there are new hydrodynamic coefficients in your non-central symmetric system, and finally we found new anomalous transport coefficients in nonlinear regime. Also, but there are some questions remain. First one, for example, what would be the effect of artificial electric field in the presence of magnetic field? You can just preserve the inversion symmetry and break the time reversal symmetry with an external magnetic field and see the contribution of these coefficients in your transport coefficients or transport conductivities, even in linear regime. And also you can generalize this theory without considering the Galilean invariance distribution. By doing that, actually, you should deal with some hydrodynamic fluctuation and hydrodynamic interactions in your system, which maybe would be interesting. And thanks. Yeah. If there is any question.
Thank you, Omid.
Thanks.
Yeah, we have plenty of time. Somebody wants to ask a question, make a comment. I understand people are tired. Is the last.
Okay, Daniel, I have a question.
Go ahead.
Hi, Omid. Thank you for your talk. I have a question, Omid. I didn't understand what exactly was the origin of artificial electric field in your work. Is it in relation with what Stefanov found about Berry curvature for Weil semi-metal? I mean, in that you demanded the particle be in instantaneous helicity basis. Was that the origin of this artificial electric field in your model?
Yeah, exactly. For example, on that work, you demand that your Hamiltonian should be diagonalized for every p, because you demand that.
Yeah, exactly.
Yeah, you demand that your Hamiltonian.
Okay, Omid, sorry, but in that.
Okay.
But in that case, a magnetic field makes the role of interaction. Is it true? I mean, the particles are under the influence of external magnetic field, and their trajectories change, and then we demand the particle be instantaneously in one specific basis. I mean, helicity basis. What is the interaction in your model? I didn't understand. The particles are interacting with what?
Actually, the role of magnetic field in I think in that case is that it makes some off-diagonal term in your Hamiltonian, right?
Yes, yes, exactly.
And but the role of interaction in, I mean, if you don't consider, let me just go back to this case. Yeah, if you don't consider interaction in your system, okay, you still have some of diagonal term in your, you can say, effective Lagrangian and Hamiltonian, right? Because you have non-zero Berry curvature, because you break the inversion symmetry, for example. Okay, but when you introduce interaction, you are able to define this artificial electric field. That's the role of interaction.
Yes, but I guess I didn't understand what exactly your interaction was.
My interaction is electron-phonon interaction.
I see.
Yeah, this is the kind of interaction that I introduce.
Okay, thanks. Thanks.
Okay. Is any other question?
Hi, can I ask a question?
Go ahead.
Hi, Omid.
Hi.
I have another question following last question. I really didn't understand. I think in the usual case, we have the dependence of the Ket and Bra, the Ket and Bra that you use in Berry connection. There was this dependence on K only. But here, on your case, you say that there is an extra dependence on this omega that came from interaction. But I didn't understand how interaction induced this dependence on omega. But is this, you should have some kind of interaction that induced this dependence, or any interaction induced this dependence, or what's the difference? What's the difference between our usual Berry connection that it only depends on K?
For your first question, I think you should only pick those interactions that produce the omega dependency in your self energy. I mean, you can use some approximation to avoid finding this omega dependency in your self energy. But here we use a specific, for example, interaction, which is electron-phonon interaction, which obviously we saw that in your real part of self-energy, we can find this omega dependency.
Is it obvious from this interaction that this dependency will emerge, or
no? I don't think so. I think you need to calculate the first order interaction and see this omega dependency. I think so. I'm not sure.
So, Omid, you mean one cannot keep track of inversion and translation symmetry and see if there's some relation between those symmetries and this Hamiltonian?
No, I mean, to have a non-zero Berry curvature, we need to break one of those symmetries, inversion symmetry or time reversal symmetry. If you have both of them, then you will find zero Berry curvature. But we just only introduced this electron-phonon interaction because we need this omega dependency to define the artificial electric field.
But sorry, but as I understand, I think this self-energy contribution always induce, if I have an interaction, there would be, at one loop, there would be this omega dependence. Is it correct, or there would be some interactions that wouldn't produce this? Can you explain a little bit more about exactly how this emerge?
I'm not pretty sure, but I think in some approximation you can find a self-energy which does not depend on frequency.
What do you mean exactly by some approximation in what?
Let me see. Okay. For example, if you consider electron-electron interactions, not electron-phonon interactions. In that case, I think in the first order term in the interaction between electron-electron for Coulomb interaction, it just change some, for example, the mass of electrons or something like that. They don't provide the omega dependency in your self-energy.
Okay, thanks.
Any other question? Okay, there's no more questions. This is the end for